Hi everyone. Today we are discussing problem number 215 of Leetcode, which is the kth largest element in an array. And in this case, say this is our array nums where we have elements 12, 5, 16, 1, 7, 55, 26, and 76. Which is our largest element here? 76. Second largest, 55. Third largest is 26, and fourth largest is 16. So, according to our question, the answer here would be the fourth largest element where k is 4. So, fourth largest element is 16. So, 16 would be our answer, right? The simplest way of doing it is, or maybe the most obvious way of doing it is to just sort the array. So once we've sorted the array, what we return is nums.length minus kth element. So nums.length here is 8. We need the fourth element from the back, so that would literally be nums.length minus k. That would be this element, and this is what we would return, right? What would be the time complexity? Because we are sorting it, the time complexity would be big of n log of n. Can we do this better? Yes, we can. And how can we do this better? We can use the min heap approach, right? Let's see how can we do this better with min heap. So what we do is we create a heap of size k. So, since k is 4, our heap size would be 4. Let's take the first four elements 12, 5, 16, and 1 and let's create a heap. Okay. So, we've all these elements here, but is this a min heap? No, it is not. So, we heapify this, right? So, what do? We first swap 5 and 1. So we've swapped 5 and 1. 1 comes here and 5 comes here. Then the next thing we do is swap 1 and 12. So we've swapped 1 and 12. Right? Is it a min heap? No, it is still not because we still have 12 and 5 to swap. So let's swap this. And we've swapped 5 and 12. And now we have a min heap. Okay. As soon as we have a min heap, we delete one. Okay, we delete one because as soon as we delete one, you remember the min heap is of size k. So for us to take another element from the array, we would have to delete one element. So because we are looking for the fourth largest element and we know this is a min heap, so obviously the element here is the smallest element and we don't care about it at all. So we delete this element and we bring in another element from the array, right? So what is the process of deleting elements from the array? Once we delete this, we delete 1 from here and we bring 12 in here, right? And we attach the new element here. So we delete 1, we bring 12 here, and the next element is 7, which we attach here. Okay. And then we heapify this. Is this a min heap? No, it is not. Right? So what do? We swap 5 and 12. So 5 comes here and 12 comes here and 7 remains here. Is this a min heap? No, it is still not a min heap because we will have to swap 7 and 12 as well, right? So now we've swapped 7 and 12. So we have 5 on top, we have 7, 12, and 16 here. Now, is this a min heap? Yes, it is. So as soon as we have a min heap now, we will again do the same thing. We still have elements in this array left, which would mean we would have to delete the element right on top, right? Because that's the smallest element that we have, smallest number that we have. So we are not interested in it. Again, the question is the fourth largest number, right? So this is the smallest element that we have now. So we delete this. How do we delete this? We remove 5, we get 12 here, and the next element that's there in the array, which is 55, gets attached here, right? So we remove the 5, and we brought 12 here and we added 55 here. Okay. And then what do? We heapify this again. So when we start heapifying this, how do we do it? This portion is sorted, we don't have to do anything. 7 is less than 55, so we can move on. Now when we come to this level, we see 7 is lower than 12. This value is less than this, so we swap them. So 7 comes here and 12 comes here and 55 remains here. Okay. Is this a min heap? Yes, it is a min heap. Do we have elements left in this array? Yes, we do. So what do? We again delete the smallest value, which is 7. Okay. We delete this, and we bring in a new element. We always bring in a new element at the end. So what do? We first bring the last element to the top, and then we add the new element here. So if we have to delete 7, we get 55 here, and we add 26 here. Okay. So we've got 55 here and we've added 26 here. Okay. Now what is the next step? The next step is to heapify it. Is this a min heap? No, it is not. So this level is sorted. 12 is less than 26, so it's okay. But is this level sorted? No, it is not. Because 55 is much higher than 12. It's a greater number. So what do? We swap the two. 12 comes here and 55 comes here, right? Is it a min heap now? No, it is not. Because 55 is greater than 26. So we'll have to swap again. So now we have 12 here, 26 here, 55 here, and 16 here. Now is this a min heap? Yes, it is. Okay. Are we done? No, we are not done, because we still have another element in this array. Okay, so how do we compare 76 with the other values? We would have to delete the smallest element. Okay, so 12 gets deleted, but to delete 12, we bring 55 here and we add 76 here. So we have it here. So we have 55 here and we have 76 here. Is this a min heap? No, it is not. So what do we swap? We swap 26 and 55. Okay. Sorry, we do not swap 26 and 55, but the smaller number out of the two child nodes 55 has is 16. So what do we swap? 16 and 55. So 16 comes here and 55 comes here. So this is what we have. Is this a min heap? Yes, it is. Do we have any other numbers in the array? No, we don't. So what do we now have? We've been deleting the smallest elements, and now we have a heap size of 4, right? In this heap size of 4, the smallest element is 16. But because we have deleted all the numbers which had values lower than 16, we know, and this heap size is of 4, with only the four largest elements of the array in it, with 16 being the smallest of all the four largest elements. We know 16 is the fourth largest element in the array. Okay. Now, how is this a better algorithm than the previous one? Because we have a heap size of k. Okay. What Every time we do a delete operation, every time we are adding this new value, what is it going to be? What is the time complexity going to be? It is going to be log of k, and because we have n elements and we are trying to insert these n elements into this array, like we are performing this operation n times, what is the time complexity going to be? It is going to be big of n log k, right? So we have, and k is less than n, so we have reduced the time complexity by a little. Now, there is another method to do these kind of problems, the kth largest element kind of problems. There is another method to do it, and that's called the quick select. And with quick select, the time complexity improves even further. Now, let's see how that happens. Okay. Now, how does quick select really work? Say this is our array, right? This is our array nums. These are the numbers that we have: 12, 5, 16, 1, 7, 55, and 77. K is 4. We want the fourth largest element. What we do now in this case is that we find a random pivot element. Okay, so for this array, say for example, we randomly picked up 55 is the pivot. Now we create three lists: mid, left, and right. What will mid have? Mid will have the pivot element. What will left have? Left will have all the elements that are greater than the pivot element. And what will right have? Right will have all the elements that are lesser than the pivot element. Okay. So when we go through this array, 12, 5, 16, 1, 7 are all less than 55. So we go through this entire array in a for loop one by one, and out of all of these numbers, these numbers are less than 55. So this goes into the right list. Okay, 77 is greater than the pivot, so it goes into the left list, and mid remains this. Now, what do we know from this? So, what we want is the fourth largest element. Okay. Now, you see this list together, okay, have the larger numbers, and they have just two elements. So, we know if we eliminate this and this, we know we have eliminated two of the largest elements. Okay. So, two of the largest elements from the array gone. Now, from this array, this is the remaining array, which is the right array. We need the second largest element, right? Originally, we needed the fourth largest element, but two of the largest elements we've been able to eliminate. So now we need the second largest element from this array. So in a recursive method now, we call the same quick select function again with the k value reduced to 2, and now the new list that we need to um, uh, uh, send in as an input parameter to this function is this right array. Okay. So let's move on. So now k is 2, nums is this, and we again randomly choose a pivot. So this time, what do we choose as a pivot? 16. Okay. And in our mid array goes in the pivot element, which is 16. If there were multiple 16s, it would have gone into the mid array, mid list. Then in left, we put everything that's greater than 16. And here we have nothing that's greater than 16. So the left list remains empty. Okay. What goes into the right? Anything that's lower than 16 goes into right. So we have 12, 5, 1, and 7 here. Okay. Again, now look at this. Okay. K here is 2. So we are looking for the second largest element. And mid and left, which contains the greater elements, together is one element. Okay. So we can again eliminate this. And now, so out of the two largest elements that we were looking for, we've been able to find one, and we can eliminate this. So every other number that is there on the right is lower than 16, right? Now, since we've been able to eliminate one more larger number from the from all the from the four largest numbers that we were looking for from the beginning, now we can reduce k to 1. Okay. And we can call the function quick select again recursively with just the right array. So now k is 1, this is nums, and we again randomly choose a pivot element. So this time our pivot element is 5. Okay. So in our mid list, what goes is every element that is equal to the pivot. So 5 comes here. On the left goes every element that's greater than the pivot. So 12 and 7 come here. On the right goes every element that's lesser than the pivot. So 1 comes here. Okay. Now look at this. Left and mid together, okay, left and mid together are greater than 1. Okay. In fact, the number of elements in left itself is greater than 1, and left is what has the larger elements. So what can we do now? This time we can ignore mid and right, and we can only look at the left array. Okay. So we need the largest element from this portion. Okay, 7 and 12. So K remains 1. We are looking for the largest one. We are eliminating everything on the right, and the mid. So we are looking for the largest element from here. So now recursively, this becomes the new input to the recursive function, and K remains 1. Okay. So k is 1 here and nums is 12 comma 7, and again we randomly choose a pivot element 7. Mid becomes 7, left becomes 12, and right is nothing because there is no element that is smaller than the pivot element. Remember, every element that's smaller than pivot goes into right, and every element that's greater than the pivot goes into left. Okay, now look at this. Left has one element, sorry, left is one element, which is 12. Mid has one element and right is nothing. Now, and the number we are looking for is the largest element, so it is pretty much here, but since there are values in left which is, and the length of left is greater than or equal to 1, we know that our value lies in this left array. So we ignore mid, we ignore right, k remains 1, and we recursively again call this array with k equal to 1. So now nums is 12, pivot has to be 12, mid is 12, left has no value, right has no value, and because pivot has mid has just one value, left and right are empty. What we do is return what is there in the mid, which is the pivot element, and we return pivot element. Okay, so this is how it basically works. So we keep eliminating either the right or the left, and at the point where left and right do not contain anything, right, we've eliminated everything else, and mid contains the pivot element. So no matter how many ever times it contains a pivot element, meaning to say if there were multiple 12s in the array, the mid would have had multiple 12s. So what we do is, at this stage, when we've reached this stage and we've eliminated everything on the left and right, what we have in the pivot is our value. Okay, k at this point will also become 1, right? So this is our value. This is the quick select algorithm, and the this algorithm costs big O of n. Now of course, that's in the worst case, of course, uh, if you choose your pivot terribly, right, if the and we choose the extreme elements, then the number of elements that we are able to eliminate really reduce. In that case, it can become an O of n square algorithm, but that never happens. That never happens. It will always be an O of big O of n algorithm. And how do we know that? Now, there's a theorem called the master theorem, right? It is for asymptotic analysis of algorithms that follow the divide and conquer rule, right? And so let's first look at the quick select algorithm, and then I'm going to explain to you why this is an O of n algorithm. So let's quickly look at this function. So if this is our quick select function, what we do is we choose a random value from nums, right? And we have a pivot index based on the random. So and we have a pivot value which is the value in the nums array, which is at the pivot index. Okay, so we've chosen a pivot. At this point, we've chosen a pivot. We've now declared three lists: the left list, the mid list, and the right list. Okay, and then we go through the numbers in the nums array. If num is greater than pivot, then we add it to the left list. If the number is less than the pivot, then we add it to the right list. And if the number is equal to the pivot, then we add it to the mid list. Now, if what are we seeing here now? We are checking if, say, suppose we need four elements and fourth largest, and and left has five elements, right? So we know the fourth, and left is what contains the larger, left list is what contains the larger values, right? And so if k is less than the number of elements in the left list, we know that left is what has our value. So we recursively call this function again with just the left list and k. Okay. Else, if left plus mid is less than k, so in the left array we have just one element, and in the mid array we have just one element, and these two lists are what contains the great higher elements, the larger elements. So we are, say for example, we are looking for the fourth largest element, and these two together contain only two of the largest elements, so we can eliminate this, right? And we've eliminated two of the largest elements. Now in the list that contains the smaller numbers, the number smaller than mid, we will look for the fourth largest, but we won't look for the fourth largest because we've, out of the fourth largest, we've already eliminated two of them. So in the right array, what we look for is the second largest, so k minus left count minus mid count, okay, is what we look for. And then we recursively call quick select again, and this goes on till a point where k is k is no longer less than the left count, because say the left doesn't have any value, and left count plus mid count is also not less than k, because mid count is what would have the pivot element, so the pivot element would be the answer at the end of it, right? So this value would definitely be 1 or greater. When there are multiple pivot elements, this count will be greater than 1. If there's single pivot element, meaning to say, if say 12 is the pivot element and we have multiple 12s in the array, then the mid count would be greater than 1. If we have just one 12 in the array, then the mid count would be 1, right? So left count plus mid count would no longer be less than k, which would basically mean, the uh, we've gone through, we've eliminated everything apart from mid. Okay, so what is there in mid is our answer, so the pivot element is the answer. At this point we return pivot. So this is our quick select algorithm. Now, coming back to master theorem, okay, let me explain to you why this algorithm costs big O of n. Now, what does Master's theorem say? Say this is a divide and conquer problem. We've already realized that. So we've been eliminating one part of the array and we are making the problem smaller every time. So what does Master's theorem say? So now say n is the total problem length, which is the total number of elements in the original array, right? Now b is the subproblem size. So each time, what are we doing? We are dividing the array into two parts. Say we are dividing them equally, may not be, but then just let's just assume. So b in this case, what do? We are basically dividing the array, the input array, into two parts. So b becomes 2 because we are breaking it up into two subproblems. Okay. Now, what is A? A is the number of times a subproblem is called recursively. Now, let's look up, let's come here. So, what does it do? So, what are we doing here? Here, we are basically checking whether we are interested in the left array or we are interested in the right array. Okay. So, if we are interested in the left array, we call the left array recursively. If we are interested in the right array, we call the right array recursively. So we have divided the problem into two subproblems, but we are eliminating one subproblem and we are recursively calling just one subproblem. Okay. So if we were in a different sort of a problem where both the right and the left had to be called recursively, then A would have been 2. But here in this case, what we do is we eliminate one part and we are interested in just one part. So A is 1. So the number of times a subproblem is called recursively is 1. Okay, because we are eliminating the other part. So we have these three defined here, n, b, and a already. Okay. Now the time complexity of to divide the problem into sub problems is big O of n to the power of d. Okay, so in this case, what is the time complexity for dividing this into sub problems? So we basically we do a random selection, and then we pick up one part, and we read one part of the array and put it into one list, and then we read the other part of the array and put it into the other list. So we traverse the array just once, right? So it will be an O of n, because we are traversing every element. It will be an O of n operation. So for time complexity to divide the problem into subproblems would be O of n. Okay, so if the time complexity for dividing the problem into subproblems is O of n, then what is d? D has to be 1, right? Only in that case will the time complexity be O of n. So we have these values here now. A is equal to 1 in our case, because the sub problem is recursively being called just once, right? B is 2 because we are dividing our original list into two sub problems, original problem into two sub problems. And D is 1 because in our case we see that to in order to break the problem into sub problems, our time complexity is O of n, but this is the formula to make this O of n. D has to be 1. Okay, now what does master theorem say? Once we have established the values of these three, we have three sorts of relationships. Okay, so if A is greater than B to the power of D, then our time complexity for the algorithm is this. If A is equal to B to the power of D, then the time complexity of our divide and conquer algorithm is this. And if A is less than B to the power of D, then the time complexity of our algorithm is this. Okay. So, in our case, what is it? In our case, which of the three is it? A is 1, B is 2, and D is 1. So, we are in the third situation, right? Because A is 1, A is less than B, which is 2, 2 to the power of 1. So, obviously, 1 is less than 2. So, for the quick select algorithm, we fall under category 3. So, according to master theorem, this is the rule of the master theorem. These three are the rules of the master theorem. So, according to the master theorem, our time complexity, or rather for quick select algorithm, the time complexity is big O of n, because D is 1. Okay, and this is basically the whole solution. So first we randomly select, we do a random selection, and then we find the pivot index. Once we find the pivot index, we find the pivot based on the pivot index from nums. Then we declare three lists, left, mid, and right, and we go through each of the elements in nums, and we add them to the lists. After doing that, we check if k is less than left count. If it is, we know that our kth largest element lies in the left array, because left is what contains all the larger elements. If that is not the case, we know it lies in the right array. Okay, so if it doesn't satisfy any of these two conditions, it means that the kth largest element lies in the mid array, which is basically the pivot element. So we return pivot.